All right, let's get started. So we're starting the first section. I took a look at the Padlet. Some people put some stuff on there. I know some people expressed concerns about they didn't do so well in their first semester biochem, and now they're worried about this semester. And I would say it's a different class, right? For instance, 445 is meant for our chemistry majors. 446 is meant for bio majors are allowed to take 446 without having to take 445. Okay. I think maybe I have a different teaching style. Maybe, like I said, in a lot of the exams are worth less, which I feel like is something a little bit different than other science classes. Yeah.
If we're taking this class with 445, then
That's okay, right? And because, like I said, right, there's a bunch of bio people here who are like, what the heck's 445? I don't know, maybe you guys know, but yeah, so it's meant to design that you don't think that comes first. There was also a question on the Padlet about like, do I have to read the whole chapter? Do I read everything, you know? And I often take this question as one of the life skills I hope you get out of being a student at Sonoma State or just in college is a lot of the content you might forget when you like cross that stage and you're done and you're out of here, right? But there's certain skills. And one, I feel like in today's world, I think about this with my kids too, is that you like all have a phone, you have a tablet, like you have so much information coming at you, you know, so much information. How do you know it's reliable, right? How do you know what to like make an opinion on, or how do you know what to make a choice on? And so that ability to sift through and pull out what's relevant and what's not, right? So my advice is always for this class, I just want you to expose yourself to the material. So if you're reading before you come into class, I'm not gonna expect you to read everything. I'm like, I don't understand that. I need to go look it up. I need to Google it. I need to watch a video on it. No, I think it's a waste of your time. Okay. If you look at the end of each section in this book, it will summarize what that section was about. So there's different levels of reading. Okay. So before you come to this class, if you read something, you're reading to expose yourself to material. You are not reading. I don't expect you to completely understand it. I know for me, the biochem book, I love biochemistry, but it's not a page turner for me. Like I remember when I first read it, I like had to read paragraph like 3 times before it like sunk in. I'm like, oh, well, that's what they're saying. And every year when I reread it, I was like, oh my gosh, it was like a deeper level, right? So if you're reading before class, again, you're just reading to expose yourself to the material, not necessarily like great understanding. So if you can, I would say read the whole thing. But if you're like, I don't have time for that, okay? Maybe you read the first sentence of every paragraph, okay? Maybe I don't have time for that. Maybe you read that end. There's like 4 bullet points at the end of each section. Maybe you read those. Read something, read the headlines, right? Expose yourself to the material, because there's going to be days when I come in here and we're talking about like phosphorylating phosphate and it gets dephosphorylated and phosphatase comes in, and it's going to sound, I feel like I'm doing tongue twisters sometimes, like Sally sells seeds still by the seashore. If you come in and you've been exposed to it, at least I feel like you'll be like, oh yeah, there was a phosphate and there was a phosphatase, and then this was, but so hopefully it will make a little bit more sense instead of hearing it cold first time in this classroom. Okay, so do what you can, but I think it's important that you expose yourself to the material before you come in this class. All right, any questions that came up for you guys since Monday? And people usually don't like today's lecture. It gets better as we go along. Okay, it does get better. But today we're going to bring up like all the stuff from like Gen Chem and OChem that is relevant to your whole kind of semester of biochemistry. And I feel like it's really hard sometimes to see it out of context. Okay, but we're going to kind of review some stuff. You've already seen it before. Okay, but we're going to review some stuff and it becomes relevant to the stuff we'll see throughout the semester. Okay, and maybe you'll love it. Okay, I love it. Maybe you will love it too. Okay. So the first section is on bioenergetics, okay, biochemical reaction types. There is, right, yesterday or on Monday, sorry, we talked about metabolism, right? And the woman in the video says it's a sum of all these chemical transformations, right, taking place in a cell or taking place in an organism. She talked about metabolism, right, the degradative phase. A lot of times we'll think about that as like sugar getting broken down to carbon dioxide and water, okay? Anabolism is that building up phase, okay? And it's all a big flow to this whole biosphere, right? You have the plants, right? They're the autotrophs, right? They can harness energy from sunlight, right? And they use that energy to create these rich carbohydrates for us and oxygen. Okay, so the autotrophs are capturing the energy of the sun. Okay, we like animals are heterotrophs, right? We have to eat the plants, we depend on the plants, right? And we break down those nutrients and we give off carbon dioxide. Okay, so it's a huge transfer of energy going on, right? Plants getting energy from the sun to make carbohydrates for us, we eating the plants, right? It's this huge transfer of energy. You guys remember what governs the transfer of energy? What governs? Huh? ATP is really important. That's one way we can transfer energy. Okay. But more general than that is thermodynamics. Okay. You guys have some thermodynamics in your life, right? Okay. So the transfer of energy is governed by the laws of thermodynamics. Okay. I'm not gonna write it down. You guys remember what the first law of thermodynamics is?
Energy cannot be created or destroyed, or is that the second one?
Yeah, no, that's first conservation of energy, right? Total energy remains constant, right? It can change form, like we just said, it went from sunlight to making carbs in the plants, to eating it, to using it, okay? But it can't be created or destroyed, okay? But it can change forms, okay? How about the second law of thermodynamics?
Isn't it like the increase of entropy of the universe?
Yeah, I feel like we really obey that in our house, right? We really obey that second law of thermodynamics. The universe is always tending towards increasing disorder. Like I try to clean up and then like by the end of the night, I'm like, oh my gosh, what you guys do? You guys are just, and then I comfort myself and say, you guys are just following the second law of thermodynamics, okay? So always increasing disorder, okay? And chemistry will talk about like if you go from like a solid to a gas, right? That's an increase in entropy. Because a gas is very finite, it's very defined. I mean, sorry, the solid is very definite, it's very defined, where a gas is moving all over the place, it's taking the shape of the room, there's a lot more entropy. Okay. There's a third one, we're not going to talk about it though. Okay, now there are 3 thermodynamic quantities that describe energy changes. These are important. You remember what they are?
Free energy.
There's Gibbs free energy. You guys remember G? Right, there's Gibbs free energy. So this tells you how much energy is available to do work. Okay. If it's positive, we say it's endergonic, right? If we have to put energy in, okay. If it's negative, it's exergonic, there's energy given off. Sometimes the units are joules per mole. They can also be calories per mole. Remember, joules and calories is the way we measure energy. Okay. You guys remember another thermodynamic quantity? Enthalpy. Okay, H. Okay. And we can think of that as some people might say like the heat content. I like to think of enthalpy as the number and kinds of bonds. Number and kinds of chemical bonds. In the reactants versus the products. Okay. Did I end up with more stable products? All right, or did I end up with more unstable products? right? That's going to depend on what types of bonds there are in our molecule, okay? And if there's a release of heat in a chemical reaction, you guys remember what we call that? Okay. Exothermic, remember exothermic, heat is given off, exothermic. You guys have had this before, right? It's coming back. So fun, okay. And endothermic is if heat is taken up, right? Okay. And a lot of times these units are in joules per mole as well. Okay. Okay, and there's one more. Yeah,
That's
S, entropy. All right, perfect. Yes. Complementary. Letter S. Entropy. And this is the way we give a quantitative value to that randomness, right? That disorder. Okay.
what are like the SI units for entropy?
Uh,
Is it meg-
they're usually joules per mole Kelvin. Okay. Yeah, you remember, and then these are all related, okay? We have an equation that describes how these three quantities that tells about thermodynamics, remember. Thermodynamics is the study of the flow of energy between systems, okay? These are the three quantities we described, okay? They're related by an equation. This equation, it's what got me tripped up when I was in grad school, and you have your oral, yeah, like your qualifying exams, like your third year, and this equation came up, and I was like, how, I would never think, but everything comes back to this thermodynamic equation, right? And you have a delta G, right? The change in the Gibbs free energy is equal to the change in enthalpy minus the temperature and the change in entropy. Okay. T is absolute temperature. Okay, so whenever delta G is negative, we say that that reaction is spontaneous. Okay, we call it a spontaneous reaction. Okay. And to get reactions to go to be spontaneous, in lab, what might we do? Like if you've been in chemistry lab, what might you do? A catalyst. What else? Heat things up. Okay. So right, by increasing temperature, I increase this negative term that has a minus sign out in front of it, which creates a larger negative value here, right? Which is going to help delta G also be negative and spontaneous. Okay. However, us humans, right? We're gonna, like, metabolism is all about all the reactions going on us. They're not all spontaneous, they're not all favorable. Well, they actually do end up being spontaneous also, but we can't heat us up, right? We're not gonna turn out the hot plate on us. Okay. We tend to operate at a constant temperature and a constant pressure. Pretty sensitive to that kind of thing. So we'll look at how does the body get delta G to be negative, okay, and the reaction going on. Okay. All right. Now something else you guys learned. So there's thermodynamics real quick, right? Okay. Something else you guys have learned in Gen Chem and OChem is that reacting systems tend to go towards equilibrium, right? You guys have learned about that, okay? They tend to react until equilibrium is reached, right? And that doesn't mean it's at a standstill. Remember, it's just the rate of the forward reaction, right? And the rate of the reverse reaction are equal. Okay, there's no net change occurring, even though the reactions are occurring, there's no net change. All right. So, you remember how we define KEQ? The equilibrium constant, right? If you have reactions. Going. Right, reactant A reacts with reactant B to give product C and product D. Remember, we can draw, I am recording this lecture, so I'm gonna try to stay not too far that way. But our KEQ, right, gets defined as right. The concentration of our products raised to their molecular coefficients is on the denominator. Is on the bottom, and on the top is the concentration of our products divided by the concentration of our reactants. Okay. You guys remember that? So systems want to go towards equilibrium. If a system is not at equilibrium, okay, and it wants to move towards equilibrium, this is a driving force. Okay, this is a source of energy that our body can use. Because we can't turn up the heat on us, so okay, we can use this concept of trying to go towards equilibrium to help drive a reaction. Okay. Okay. So you guys have probably learned about the standard. There's a lot of standard constants. So we can have a delta G with a naught. Okay, and these are things you can look up like in the chemistry and physics handbook, right? The CDC, you can look them up. You can look up constants of certain reactions, okay? Because there have been a set of conditions defined for these standards, okay? And the conditions are 25 degrees Celsius, 1 molar, everything's at 1 molar, the concentration of everything's at 1 molar to start. Okay. Pressure is at 1 atm. These are the definitions for our standard constants. We have to define the conditions to be able to have constants we can look up. However, this doesn't work for biological systems. Okay. So for instance, if you had 1 molar protons, okay, so we'll talk a lot about the movement of protons, and if they were at a standard condition of 1 molar, that would be really, really acidic. Okay, so that doesn't work. So I just want you to know there's a different set of definitions for biological systems, and we call these the standard transformed constants. Okay. So we mark it with an apostrophe and the not. Okay. Standard transform constants, and here we define the proton concentration is going to be 10 to the -7 molar. Okay, concentration of water. You don't have to memorize these. I just want you to be aware that in biological systems, there's a different set definition for the standards. And so when you see this apostrophe, okay, that apostrophe signals the standard. I don't know why they transformed constants. Okay. So again, these are just for biological conditions. Okay. I bring that up because we can relate our delta G a standard transform delta G, and KEQ. Okay, and you guys have learned this already too. Okay, the relationship between our standard free energy and our equilibrium constant. Okay. So the relationship delta G, right, standard and transformed, meaning biological conditions, is minus the constant R times temperature, natural log of KEQ for our biological systems. Okay, have you guys ever seen that relationship before? Remember that one? Again, so it's a way to, it's a different way to express our equilibrium constant. It also relates our Gibbs free energy to our equilibrium constant. Remember, our equilibrium constant is defined by our concentration of products and reactants. Okay. Okay. Now there's a little bit of math we got to remember for some of this to make sense. Okay. You guys, so if I have, if my concentration of my products are lower than the concentration of my reactant, right, I'm going to get a number that's less than 1. Does that make sense? Right? If this is a smaller number than this, I'm getting something like 1/2 or 3/4. Right? It's a number less than 1. Okay. If I take the natural log of a number less than 1, do you know like what kind of number? What do I get?
A positive number?
Other way. And thank you, I appreciate it. Okay. So if you guys, I don't know if you guys remember, but natural log of 1 equals 0. Okay. Natural log of a number that's less than 1 is a negative number. Okay. Natural log of a number greater than 1 is positive. Okay. Who cares? Why do I care? Why do I bring that up? Okay. Yeah, it's gonna help. It's gonna tell us what's going on here. Right? Okay. And a little bit farther we gotta go though. So just remember that natural log of a number less than 1 is negative. It's going to be less than 1 if my products are less than my reactants. Okay. Natural log of a number greater than 1 is positive. That's going to happen when products are greater than reactants. Okay. Okay. Now, this right here, delta G apostrophe naught, okay, is a constant. Okay, we can look it up in a book because it doesn't change. Okay, it's for a set of defined standard conditions. Okay, but if we want to understand what's happening like in an existing cell, okay, we need the actual free energy. Okay, and the actual free energy is just represented by delta G. Right? No apostrophe, no not. That is our actual free energy. Yeah.
So just to clarify, kind of got lost with the delta G not. That's for standard conditions, but then when it comes to delta G apostrophe not, standard like in a biological system set in standard conditions.
Yeah. So coming into this class, you probably have seen this delta G naught. Okay. Such your standard free energy. Okay. But again, this has certain conditions defined. And again, as chemists, right, we're like, okay, we're fine with those standard defined conditions. But when we bring those standard conditions into biological settings, and no longer like it's just not relevant. So then they have this standard transform. So there's still standards, right? But there's a little bit of difference we have to make. And like one of the most like this one really sticks out to me. Because again, if we have 1 molar H plus, like it's very low acidity, which is super not relevant to like humans, right? Maybe there's some acidic bacteria that thrive in those conditions, but for the most part, a lot of the organisms we study are not going to be existing in those acidic conditions that would be defined with like the standard conditions we bring from like straight chemistry. So this is, I think, more relevant to biochemistry.
I was also wondering, for the equilibrium constant, is the number one always defined as equilibrium, because that means that the reactions are the same, or is every equilibrium different or different?
No, so you're saying like is KQ equal to 1?
Yeah, if one
Mean-
means equilibrium.
No, right, because for it to be 1, that would mean that concentration of products and reactants are the same. And so that is not the definition of equilibrium, right? So, if your KEQ equals 1, that just means that the concentration of your products and reactants are the same. But like KEQ can be equal to like 0.5, or it can be equal to 2.7, right? So there can be, and that could be at equilibrium. And it just gives you, like, if it's 2.7, that tells you products are favored, right? It's a number greater than 1. If it's 0.0027, that means, okay, reactants are favored, because this is a larger number. Thank you, I appreciate it, because I know, like I said, I feel like this today is a lot of review. I'm like, why are we talking about this? I thought we were in biochemistry. But I promise you, when we start looking at the reactions, we're gonna, like, this is gonna help us understand why the body is doing some of the things we do. And it helps us, I feel like, move away from like feeling you have to memorize everything. Maybe you start there with memorization, but then if you can think chemically about it, then it like brings it a whole new level. Like, oh yeah, it's trying to get negative delta G, so it can be spontaneous, and that's why it's doing whatever it is it's doing. That's why our oxaloacetate concentration is so low. Okay, so I promise it will become relevant later. Okay, other questions? Okay. So like I said, yes, so standard coming straight out of chemistry. Standard coming out of like standard transform for more biological conditions. And this is actually what's going on, right? We can't look this one up in a book. There's no, this is like what's actually, like I'm studying something, what's actually going on. Okay. So there's changing conditions here. It takes into account the actual cellular concentrations, the actual temperature, okay? And this is defined, okay, by that standard transformed, okay, plus RT, natural log of Q. Ooh. You guys remember what Q is? You see Q?
Like heat.
Lowercase q.
Oh.
It sometimes represents heat. Yeah. I love it.
USK, not at.
So it's like K, it's just like K, but we're not at equilibrium. Exactly. Okay. So it's called the mass action ratio. I don't know that name. Okay. And it's the actual concentrations. Okay. So Q, these are technically all at equilibrium. Sorry, I shouldn't include that. When you're talking about KEQ. Q looks exactly the same. Okay, but you're not at equilibrium. Yes, it's the actual cellular conditions. Okay. Okay. So sometimes when we're looking at reactions, the standard transformed Gibbs free energy might be positive. Okay, it might be positive. And we're thinking like, oh, that reaction is not spontaneous. Okay. But what's actually going on in a cell is defined by this. Okay. So I'm going to be quiet for a minute. And I'd like you guys to talk to somebody, I think it's a group assignment, and I want you to think about looking at this equation. Okay, focusing on that one. Oh, man. You guys see that question? I don't pull this down. Oh, yeah. So how can a reaction be spontaneous if the standard transform delta G is positive? Okay, so you guys get that question. First, it goes right there. Right. Wow. Okay. Okay. Yeah. And just so you guys know, this is a group assignment in your Canvas course that's due by midnight tonight. Yeah. You can tell. Yeah, that's much way to look.
Small, right? You just thought it would be super small. Super small. Okay.
Yeah. The reason why I said short is
Yeah.
Well, the product. Yeah.
Yeah, you wanna, what you want, but.
Q will be less, community will less than one, and then, That's the only number that you can the whole vibration.
Okay, you guys hear what Milana said? No, okay, she said if the concentration of the products are really low. Okay. The concentration of the products are low. That means our Q will be a number less than 1. And since we're taking the natural log of Q, we said the natural log of a number less than 1 gives us a negative number. So that can turn this, right, this whole term, this RT natural log Q term, negative. And if it's negative enough to overcome whatever, this is a positive delta G, standard delta G, then the actual delta G can become negative. Okay, so this is a technique the body utilizes. It might keep the products of a certain reaction low if it's a non-spontaneous reaction to help drive it forward. Okay, so again, like I said, something that will come up is oxaloacetate. Okay, we'll see it at in gluconeogenesis and making glucose. We'll see it in the citric acid cycle. Okay, we'll see it a lot. But your body tends to keep that low, and part of that is this reason. Okay, if it keeps it low, it helps drive non-spontaneous reactions forward. Okay, there's a second question in your group activity. Okay, that I'm gonna let you guys think about it. I'll tell you what it is, but you can think about it. And it is you know, we said the second law of thermodynamics is that the universe is tending towards increasing disorder, right? We want to be disordered. However, if I look at myself, I look pretty ordered. Okay, like I got all these cells organized into a liver, and I got all these cells organized into a heart, and I got all these cells organized into fingers. Like I'm like pretty ordered here. Like, so think about that. Do living organisms, are they disobeying that second law of thermodynamics? Okay. Are they disobeying that second law? They're so ordered. Okay. You guys can think about that and make sure you put that into the group assignments due tonight by midnight. And again, if you don't get to it today, just please do it at some point. I will grade on it. They'll be part of your grade. Okay. Okay. Other questions? Yeah.
That question, would you like us to come up with an example of an organism or just with the textbook?
I want to know, what do you think? What do you think?
Probably.
Not necessarily the textbook, not, yeah, like just, what do you think? You think they do this with thermodynamics or what? And why or why not, right? Try to, why do you think that? It's just a thought process to think about it. Okay. Okay. Now, we've been talking a lot about thermodynamics, okay? You guys remember when you talk about thermodynamics, a lot of times they'll say, we only care about what you start with and what you end with, right? A lot of times, I don't have an eraser. But a lot of times you'll see your delta G represented graphically. Right? You guys have seen diagrams like this. It's called the reaction coordinate. Okay, and you might see something like something like that. You guys see, and you see like this is your reactants, right? These are your products. Oops, sorry, this is right. This is telling you like, okay, your reactants have this much energy, your products have this much energy, right? And the difference between their energy, right? You might call it a delta G. You guys remember seeing that? Okay. So again, this is thermodynamics. It's really only concerned about where did it start and where did it end up. It's not really interested on how you got there. Okay, and this is an example where the energy of our products is greater than our reactants, right? This is a endergonic reaction, right? Energy will get put into the system to get to those products. You've seen this represented the other way, where maybe the energy of the reactants is higher than the products. Okay, and again, we call this the difference in energy, the delta G. Okay, I bring that up just to demonstrate that in thermodynamics, and you guys have heard this before, you're really concerned about where did your system start and where did your system end. Not how we got there. You guys remember what field is concerned about how you got there? The path of it? Yeah, kinetics. Okay, so kinetics is concerned with how did you get there? Okay. So a reaction might be spontaneous, right? Meaning that the energy of the products is less than the reactants, okay? But it could occur very slowly. It might be happening very slowly, and that's described by the kinetics, okay? Just like wood, right? It's spontaneous for wood to break down, okay? But we could look at a piece of wood and it's not just gonna happen, okay? So we need, right, you have that activation energy, right? That activation energy is there. So sometimes you might put a match to it and give it some energy and help that process along, okay? Okay, so in our systems, someone said earlier, catalysts, right? Catalyst helps drive reactions forward. That deals with the kinetics of a reaction, okay? We have enzymes. We have enzymes that help lower activation energies and allow reactions to occur at rates that we need. Okay, so we don't have necessarily catalysts, but we have enzymes. Remember, they don't affect equilibrium. They're not messing with the equilibrium with the thermodynamics. They're affecting the kinetics, the rate at which these reactions occur. So thermodynamics determines direction. Kinetics determines the rate. Okay. Okay, I'm going to. Any questions on that? Okay. So something that we can do with our delta G's is they're additive, okay? We can take one reaction that goes from A to B, okay, and couple it with another reaction, okay? And to figure out what the overall delta G is for that reaction, we can just add those two delta G's. So that's another technique the body will use to overcome a non-spontaneous reaction. So if we have one reaction that's negative and one reaction that's positive, as long as the negative reaction is more negative, right, it can make the overall reaction negative. So again, we're going to be looking at examples of this. I just want to remind you guys that this thermodynamic quantity is additive. We can add them. Okay. All right, so let's look at we're just gonna kind of remind ourselves. So the way we'll be transferring this energy, we'll be making a lot of bonds and we'll be breaking a lot of bonds. Okay, when we go through all these chemical transformations. Okay, and so there's just some terms. I want to make sure we're all on the same page. Again, you guys have probably seen them. So common terms you might already know, right? But I don't know if you think about it, right? In that first one, we have hydrogen atom. Hydrogen atom, okay? Hydrogen atom, right? One proton, one electron, okay? Also a proton, right, is different than a hydrogen atom. A proton, right, has no electrons, okay? It just has a proton. Okay, so we're gonna be thinking about the way we represent when we just write, there's gonna be a lot of proton moving or maybe a hydride or a hydrogen atom. We want to be thinking about, you know, is it an atom, is it a proton, or is it a hydride, right? Hydride, hydrogen with 2 electrons on it. Okay, and a negative charge because there's only 1 proton. Okay. There's different ways bonds can be broken. So homolytic cleavage, okay, meaning each of the resulting products each got an electron. So here, remember 2 bonds and an electron. So here we end up with a carbon radical. Okay. We can have heterolytic cleavage where again 1 atom got both electrons and the other one didn't get any. So remember carbanion. A lot of this will be happening like these are the transitions, right? How we get from making 1 bond into breaking a bond to making another bond. Okay. Or we might end up with a carbocation, right? The carbon atom didn't get any of the electrons in that 4th bond, and it all ended up on the hydrogen. Okay. You guys remember nucleophile? The carbanion ions can be considered a nucleophile. Remember, nucleophile means it's nucleus loving. Okay, it loves the nucleus. What's in a nucleus? Proton. Okay, protons are positive. Okay, so negative thing is going to be loving the positive thing. Okay, so this is a nucleophile. Okay. Electrophile, a carbocation is considered an electrophile. Electrophile. Electron loving. Okay, phile means they love that. This carbocation is very electron poor. Okay, so it's going to seek out electrons. Okay. So again, you guys have seen this in OCHEM. Before I just want to remind you guys to make sure we're on the same page. Okay. And the book will talk about some other rearrangements, free radical reactions, retransfer reactions, oxidation reduction. We're gonna look at those too. Okay. So this is an example of a nucleophilic, right, carbon-carbon bond formation reaction, making a carbon-carbon bond. Okay. Notice, right? What is the nucleophile here is going for the carbon of a carbonyl. Okay, you guys have learned, right? Oxygen is very electronegative. Okay, it likes to pull electrons towards itself. We know there's a dipole in that carbonyl bond, right? The oxygen pulling electrons away from that carbon. You know, there's a partial positive charge on that carbon. So yeah, that nucleophile is like, ooh, I'm looking for that, you know, that positive charge. Okay. So this is you guys, an aldol condensation. Okay. Same thing going on here, right? We have a carbocation going for the carbon of carbonyl. Notice that causes this bond to break. Okay. All right. And then here we have a decarboxylation. We'll see lots of decarboxylation going on. Okay. So electrons here pushing on this carbon oxygen bond to make CO2 and forcing this bond to break. Notice what you're seeing represented by those arrows, right? This is showing you the formation of a carbon-carbon bond. This is showing you the breaking of a carbon-carbon bond. Okay, a decarboxylation. Okay. So there's this really interesting thing that happens. Okay. Again, why are we talking about this? Because as you can go ahead and memorize those 10 steps of glycolysis. Okay. And that's probably where you want to start, but don't end there. Okay. you start to think about the chemistry and what needs to happen. And then it will start to, you like, well, the molecule needs this to happen in order for that next step to happen. In order for that next step to happen, this has to happen. If you understand the chemistry, then you can like figure out the reactions, okay? So when we start looking at glycolysis, the first thing, right, glycolysis is the breakdown of glucose. Glucose comes into the cell, gets phosphorylated, first thing that happens because glucose 6-phosphate, okay? What's going to happen later, maybe you guys already know this, is that glucose is a 6-carbon molecule, it's going to get cut in half, okay, and become 2 3-carbon molecules. And that video we watched on Monday showed you get pyruvate. Pyruvate's a 3-carbon molecule, okay? So we got our glucose 6-phosphate, okay? Here's the open chain form. Notice the carbonyls on carbon 1 here, okay? The second step in glycolysis is we get an isomerization, okay? We go from glucose 6-phosphate to fructose 6-phosphate. And notice what happened there, okay? What happened? The result of this is a movement of the carbonyl group, right? The carbonyl went from being on carbon 1 to being on carbon 2. Okay, that's what happened. That's what the result. Why? Because eventually coming up, that carbon's going to get attacked. Okay, it's your body strategically places carbonyls, and in fact, in this case, it's actually the bond's going to break here, and having that carbonyl is going to allow for electrons to be distributed throughout. Okay, that carbonyl. So this shows you, you'll see a lot of these. I'll go over some mechanisms, but not all of them. The chemistry students tend to like them, but let's see. Okay, so represented in your book and in the diagrams on the slides, you'll see things like this, B1. What's a B1? It's just a generic base. You have to remember that these are reactions happening in your body. We said we have enzymes to help us. Remember, enzymes like a huge protein, right? There's all these amino acids connected and folded into this 3-dimensional shape, and they're forming, there's all these amino acids that are present at this active site where this reaction is happening, right? Some of our side chains of our amino acids are acidic, and some are basic. Some can act as an acid, some can act as a base, okay? And instead of telling you what amino acid is here acting as a base, you just write B1. Okay, so that's like some basic amino acid side chain acting as a base, and it's acting as a base because it abstracts a proton. Okay, and then it shows you that when you abstract this proton, this allows for the formation of this carbon-carbon double bond. Okay, and over here, there's another generic amino acid. Okay, that's acting over here to help. This is how enzymes help our reactions proceed. Okay. So electrons from the carbonyl form this OH bond, okay, with the hydrogen donated. So now you can see we have that carbon-carbon double bond, we have that OH. Now this base, that's just again a side chain of an amino acid present at the enzyme active site, can take off a proton, okay, and then that's going to allow formation of the carbonyl over here, okay. So we can see how we can move the carbonyl from carbon 1 over to carbon 2. So isomerizations, eliminations are an important part of the reactions that will happen, that we'll see. Okay, here's another discussion. And actually, well, again, just think about, see what happens when the CC bond breaks between, okay, 3 and 4, okay? Okay, this is a good group discussion. Let's look at this. Like I said, we're getting ready to split. This is the beginning of glycolysis, which we'll talk a lot about, but again, I'm just getting you guys ready. 6-carbon molecule, which we're going to split in half, okay? So now that we move the carbonyl over to carbon 2, what happens when this carbon bond breaks between carbons 3 and 4? Okay, what happens? Yeah.
Are you saying that's what happens next, or does the carbonyl have to move over one more time?
That's, so the carbonyl will not move over one more time. But if you break a bond here, right, then you have electrons, right? You have electrons in the bond. And so you guys have learned that you can represent a carbonyl in different ways. Okay, and sometimes the electrons can be on the oxygen as O minus. Okay, so that allows for some distribution of electron density through that carbonyl. It helps stabilize a carbanion here during the breakage of that carbon-carbon bond. By moving the carbonyl over, it helps to stabilize the formation of a carbanion here. Yeah.
I just had a clarification question on the previous slide.
Okay.
Was G just a mechanism for A? That's not how that's laid out?
Yes, yeah, this whole section down here, yeah, is just explaining how you got from glucose six phosphate to fructose six phosphate. Yeah, and you'll see that, excuse me. You'll see that in the slides. Sometimes the mechanisms are given. Like I said, I'll go over some of them in class, but I won't go over all of them. And but they are there. You guys can see that. Other questions? Okay, let's see. All right, so that's formation and breakage of carbon-carbon bonds, okay? A molecule we'll look at a lot, and it got brought up, I think, Jasmine, I think you said it about ATP, right? And we're talking about transport of energy, is the hydrolysis of ATP. Okay, it's highly favorable under standard conditions. Okay, so let's look at ATP real quick. Okay, ATP will be in a lot of our discussion. Okay, and if you look at it, right, if you guys have seen this before in your other classes, like adenine is a nitrogenous base. Okay, it's connected to a ribose ring. Okay. And then it has these three phosphate groups. Right? And those three phosphate groups, right, have the negative charge, negative charge, negative charge, negative charge. Okay. So when we hydrolyze ATP, here we have the water. Okay, it's attacking that last phosphate group. Okay, and it breaks that bond. Okay, so it removes, it dephosphorylizes. Okay. And then you get a phosphate group on its own, and you end up with ADP, right? So now you have adenine, ribose, and two phosphate groups here, and just a 2 minus. Okay. Now let's go back to thinking about the thermodynamics. Thinking about the energy of the reactant and the energy of the product here. Okay, if we think of ATP as our reactant, and ADP as our product in this hydrolysis reaction, right? Which one do you think is higher in energy? ATP. The ATP is higher in energy. Okay. There's our ATP a little bit up close. Okay. The ATP is higher in energy. It has all this negative charge that is just repelling each other, okay, making it unstable. Okay. Here is our ADP, okay? It's got a lot less negative charge. So we help by hydrolyzing ATP, okay, we relieve some of that electrostatic repulsion. Okay. Now, the products are further stabilized by other mechanisms. Okay, so that phosphate group we removed from the ATP, it has resonance structures, right? You can imagine writing the structure a couple different ways. So it also has resonance stabilization. Okay, The ADP can also be stabilized through ionization, okay? So this proton can come on and off, okay? We'll say that again.
Resonance stabilization if the becomes available after the hydrolysis.
After hydrolysis, yes, so it's in the products, right? The products can get stabilized. So when we look at that overall reaction, ATP being hydrolyzed by water, giving ADP and phosphate, right? Look at the delta G is negative 30.5 kilojoules per mole. So we'll use that a lot in our discussions, okay? Okay. Your cells tend to keep the concentration. Oh. That is in the plate there. Right. That should be the concentration of ATP is much higher than the concentration of ADP. Let me change that. Why do cells do that? Why would cells keep the concentration of ATP much higher than the concentration of ADP?
You can make ATP from ATP.
Yeah.
It's a way of storing energy.
It's a way of storing energy. So how do we relate? Sorry, guys. Okay. How do we relate the concentration, right, to the energy? Yeah.
It causes the free energy to be positive and be spontaneous.
Right. So, right. If we think about our discussion back here, right? And ATP is our reactant and ADP is our product, right? Well, then, if this is high, right, our concentration of ATP is high, this gives us a number less than 1. Natural log of a number less than 1, negative, right? And that can help contribute to a negative RT natural log of Q term, bringing our actual delta G's, helping them be negative. Okay. So, and it's a weird to think about, but we tend to keep the concentration of ATP high. Okay, because of this, it's a product in this hydrolysis reaction, and this gets coupled with other reactions, and it keeps it high so that our actual delta G's are low. Okay. And it all goes back to that conversation we had about delta G's and natural logs. Questions about that? Yeah.
Yeah, just clarifying, so
Yeah.
it would make Q negative, right?
Yes, so make Q negative. Let's go back and look at this. We look at this, like here's what the reaction looks like that we just talked about, the hydrolysis of ATP. Notice ATP is a reactant. Okay, ADP is the product. Okay, so when we look at Q, right, our products are on the bottom. We keep that ATP high, that gives us a Q less than 1. Does that make sense when I'm saying that? I know, I feel like it's a lot more, I'm asking you to make a lot of connections between your math, your gen chem, and then bringing it to the biochem part. Okay, bringing it to think about ATP. Okay. And again, like as we're reviewing a lot of stuff right now, as we start to see the actual reactions that are happening, I promise you, it becomes a beautiful story. Okay, it really does. Yeah.
I feel like, I think I understand why concentration of ATP would have to be higher. I just feel like the delta G is already negative, so why would it not be spontaneous?
It's not always negative though. Oh, for this reaction, it's already negative, right? So yes. We love this reaction. Remember, this is thermodynamics, transfer of energy, right? A lot of transfer, and you probably heard it in your biology classes, like ATP is the currency of your cells or the currency of your body, okay? Because of this reaction, because it does provide so much energy. So if you couple that to another reaction that has a positive delta G, right? You can add them. Remember, that's what we said, delta G's are additive, and you add them a lot of times. This will make the overall transformation negative and spontaneous. Yes, so that negative delta G really helps. So by having concentration high, it provides even more like power, more energy. Okay, yeah, that's. Thank you for bringing that up. Okay, other questions? Yeah.
I'm just curious, if you scroll up a little, so like do the hydrolysis part. I was wondering what stops the water from hydrolyzing, like say like phosphate group more to the right? Is it like enzymes that just make sure?
Yeah, so a lot of it is positioning, like again, these are all the reactions we'll talk about are going to happen within the active site of the enzyme. But sometimes it does attack other places. So sometimes, yeah, the water might attack here. And then you're going to end up with a pyrophosphate, and it's often represented as PPI, and AMP. Okay, so that can happen. Yeah, so that, and I think most of the time we see it at this position, but yeah, it can happen at other positions. And that's going to depend on the placement in the active site. Other questions? Okay, so ATP is the most common phosphorylated compound that we spend a lot of time, we just spent a lot of time talking about it. I don't expect you to like memorize this, but I want to bring it to your attention that there are a lot of phosphorylated compounds that have this large delta G for hydrolysis, okay? So there are other compounds that also have that characteristic that we talk about ATP, okay? And again, what happens, like PEP, we'll see the PEP and when we talk about glycolysis, it's the second to the last step, okay? When we hydrolyze PEP, okay, same thing, we get pyruvate, which is the product of glycolysis. Pyruvate is stabilized by tautomerization. So there's another way to stabilize the products, okay? Look at that, I don't think you can see it here, but look at that delta G, ooh, -61, okay? So getting pretty. So there are other phosphorylated compounds where this delta G of their hydrolysis plays a role in metabolism. Okay. We'll also see the hydrolysis of bioesters, okay, a lot. So acetyl-CoA, really important molecule, okay. Later on, I'll show you that the CoA is like, it's this huge coenzyme A molecule, okay, that is often just shown as CoA, okay. But again, if we if it undergoes hydrolysis, okay, you end up like here, you end up with acetic acid. The acetic acid is stabilized by ionization, okay? So again, hydrolysis of esters can also provide a negative delta G. So we'll see this a lot too in the reactions we look at more than once, okay? And so all we're just looking at these reactions, looking at the delta G's and saying like, yeah, the products are stabilized, okay? And the reactants are less stable. And so therefore we end up with this negative delta G. And we're going to use that to our advantage to help drive other reactions in the body. Okay, what time is it? Okay, so let's see. Yeah,
I have a question.
Yes, please.
For the suggested homework, this is in the chapter 13, right?
Yes, it is. Yes, it is. Okay. Okay. So you guys, we talked a lot about the flow of energy. Okay. We talked a lot about the flow of energy. And so now the next section of chapter 13 talks a lot about the flow of electrons. Ooh, redox reactions. I used to hate redox reactions as an undergrad. I don't know how you guys feel about it, but I didn't like it. But after I got to take, like, this is my 10th year getting to teach this class, like, I love redox reactions. They're very important. Okay. And so if you think about anything like the lights, your phone, your computer, it's all powered by a flow of electrons, right? There's this flow of electrons occurring that's powering these things. Well, guess what? So are we, right? We are also powered by the flow of electrons. So what kind of reactions, does the flow of electrons fall under? Redox reactions, reduction oxidation reactions. So that's where we're going next. Okay. We have about 4 minutes. Okay. There is a table, 13 and 7. Let's see if I can get these both up. But so in this group discussion, and this is just going to prime you guys, we're going to get primed up and bring back our redox. Okay. I know we covered a lot of past stuff. And you're like, really, we're gonna go over redox too, but I just want to we'll talk more about it next Monday, okay? But I want you to think about how we represent reduction potentials. So I think. Okay, so there is a table. Reduction potential, there it is. Okay. Okay. So I don't know if you guys can, that's horrible, but you guys have seen this before. Okay, you've seen these in your Gen Chem classes, and I remember I hated mapping, but I don't want to look at this. Okay, but now I feel like I don't know, I feel like maybe I didn't appreciate it then. So this says half reaction, right? And then it says, right, E energy in volts. And notice it's an E apostrophe not, right? Telling you we're in this biology, the standard transform constant. Okay. So the group question asks you to look at some oops, sorry. The question asks you to look at these different products, right? Alpha ketoglutarate and carbon dioxide, oxaloacetate, oxygen, and NADP+, and list them in order of increasing tendency to accept electrons. Increasing tendency to accept electrons. Okay. Now you can't see it, but this is okay. Now you can. It says standard reduction potentials. Standard reduction potential. So you learned about oxidation and reduction. What'd you learn? Like, what is oxidation? What does that mean? Loss of electrons, right? You guys learned something like oil rig, or Leo the line says GER to remember that. Okay, so oil rig oxidation is loss of electrons. Rig. So what's reduction? Gain, right? Reduction is a gain of electrons. Okay, so this is a standard reduction. This is a table of standard reduction potentials, like the potential to reduce. Okay, so what is represented here, right, is a molecule's ability to accept electrons. Okay, that is what is represented in these reduction potential tables. Now, sometimes I think what gets confusing is what we just had this discussion on Gibbs free energy. And like we're saying, like, you want a negative free energy, okay? But in reduction potential, it's like, it's true. Like, the more positive the number is, the more potential it has to gain electrons. Okay, so notice that this goes from the largest number, which is 0.816, and it's in order by, it's in numerical order, down to negative 0.432. So again, things, and you're looking at the molecules to the left of the arrow, okay, so it's telling you, like, this is NAD plus's reduction potential, its ability to gain electrons and form NADH is negative 0.32. Okay, notice oxygen's at the top, right? We'll learn oxygen is the ultimate electron acceptor. It has the highest reduction potential. That means it has the greatest ability to pull electrons to itself. This is why we need to breathe. Right? It is the ultimate electron acceptor. Okay, so I'll be quiet, but that's just timing you guys, because on Monday we'll talk about redox. Redox governs all of metabolism. There's so much redox in there. And it's really cool, and I hope that I'll pass on that enthusiasm to you guys. You guys have any questions? Yeah, so I opened up the group assignment. There will be a pre-assignment due on Monday. I'll open that up for you guys. Okay,
No.
so just check Canvas. So, yes. Other questions? What?